Hello everyone, my name is Maria Jaralambos and today I'm going to talk to you about remote sensing of sea surface temperature. This is an animation showing patterns of global sea surface temperatures from 1997 to 2007. It is taken from the US National Oceanic and Atmospheric Administration, also called NOAA. The general pattern shows a warmer sea surface temperature at the equator where there is a net accumulation of energy, while it is colder towards the poles where there is a net loss of energy. So what exactly is the sea surface temperature? It is a water temperature close to the ocean surface ranging from 10 micrometers to 10 meters. Since the oceans cover more than 70% of the Earth's surface, sea surface temperatures affect the air masses directly above, playing a major role in local and global weather patterns. Therefore, it is vital that they are measured and monitored reliably and accurately. Sea surface temperature measurements are important for climate modeling and for the study of the Earth's heat balance. They provide an insight into the atmospheric and oceanic circulation patterns and anomalies, such as El Niño, which I will talk about later on as my case study. Sea surface temperatures can also be used for more local weather patterns, such as the creation of eddies, fronts, and upwellings, helping in weather forecast, marine navigation, and tracking of biological productivity. Traditionally, the sea surface temperature has been measured by buoys and ships. These methods are not scientifically reliable, as they don't really measure the sea surface temperature, but instead measure the temperature at the depth of a few meters. As shown on these graphs, both their spatial and temporal coverage is very limited. However, thanks to remote sensing, more frequent sea surface temperature measurements and global coverage are now offered by satellites. Sea surface temperature can be obtained using two kinds of radiometry, the thermal infrared and the microwave. Each one has different strengths and weaknesses and can be used for different applications. The first way of measuring sea surface temperature is by using thermal infrared radiometry. The wavelengths used range from 3.7 to 10 micrometers. Unfortunately, both these bands are sensitive to the presence of clouds, scattering by aerosols, and atmospheric water vapor. Therefore, they require atmospheric correction of the retrieved signal and can only be made for cloud-free pixels. On a more positive side, thermal infrared measurements have had a long heritage of 20 years. Also, the resolution and accuracy is very good, allowing for more detailed measurements. This is a thermal infrared image of sea surface temperature with the white pixels showing how clouds block the way. Some of the thermal infrared instruments used are the advanced Very High Resolution Radiometer on NOAA Polar Orbiting Operational Environmental Satellites, the Along Track Scanning Radiometer aboard the European Remote Sensing Satellites, the Geostationary Operational Environmental Satellite Imager, and the Moderate Resolution Imaging Spectroradiometer aboard NASA Earth Observing System Terra and Aqua satellites. The second way of measuring sea surface temperature is by using passive microwave radiometry. Microwaves are of longer wavelength and thus have a lower signal strength on the Earth's Planck radiation curve. Therefore, their accuracy in resolution is poorer compared to that from thermal infrared measurements. The infrared instrument shows a root mean square error of 0.76, while the passive microwave instrument has a higher error of 0.9, and thus it has a higher bias as well. However, an advantage gained with passive microwave is that the radiation at these longer wavelengths allow it to see through clouds and are therefore better for correcting for atmospheric effects. A disadvantage of the passive microwave is that the return signal is affected by wind-generated roughness at the ocean surface and precipitation. However, this can be corrected for by using multiple frequencies. Some of the passive microwave instruments used are the Scanning Multi-Channel Microwave Radiometer carried on Nimbus 7 and CSAT satellites, the Tropical Rainfall Measuring Mission Microwave Imager, and the Advanced Microwave Scanning Radiometer instrument on NASA Aqua satellites, as well as on the Japanese Advanced Earth Observing satellites. These two images cover the same time period. As you can see, the thermal infrared composite on the top has a lot of white patches where cloud-free pixels could not be obtained over such a short period of time, while the microwave composite at the bottom can see through clouds but has a lower resolution. Sea surface temperatures when measured from space represent a depth that is related to the frequency of the satellite instrument. Up to 10 micrometers, it is a so-called skin sea surface temperature that can be achieved by infrared attenuation. Up to 1 millimeters, it is a sub-skin sea surface temperature that is achieved by microwave attenuation. Further down, up to 10 meters, the bulk sea surface temperature is traditionally collected by buoys and ships. These two graphs show the temperature gradient during nighttime on the left and during daytime, where solar radiation is strong, on the right. Therefore, the closer to the surface the measurements are done, the more accurate they are, as diurnal differences are minimized. However, this also shows that it is hard to combine different datasets together, as measurements are done at different depths. As explained before, one of the main reasons that sea surface temperatures must be continually monitored is the weather patterns and anomalies such as El Niño southern oscillations. This is a pool of warm water that forms along the equator and travels eastwards, causing severe storms and flooding to the west side of South and North America and drought in Australia and Indonesia. It takes place every 2 to 7 years and its reliable prediction has yet to be achieved. In 1997, torrential downpour raged over the western coast of America, causing landslides and destroying homes, leaving 100,000 people homeless and costing billions of dollars. However, social problems were not the only issue caused by the El Niño. Wildlife was also disrupted, as the warm water changed circulation patterns, sending fish to the colder, deeper waters, disrupting the food chain, as birds and seals could not survive without fish. Therefore, forecasting weather anomalies such as El Niño is an important task for scientists. Satellite monitoring of the sea surface temperature plays a vital role in the prediction and therefore better management of such catastrophic events.